Hello, it's What the Doodle here, and in today's session, I just wanted to do a live capture of me compiling this particular project, which is this one, which is krunvm. And essentially what this does is it takes any OCI compliant image, which is a container image, and convert that into a VM, specifically a virtual micro machine or VMM. And virtual micro machines are exciting because they are the technology that fires, for example, Firecracker, which is written by Amazon. And they're the things that power. So when you use AWS Lambda and AWS Fargate, and also things like it's in the industry, it's used quite a lot, like, for example, Fly.io, Kata containers, and a whole load of other things. And in fact, I believe when you use GitHub Actions, behind the scenes, you are most likely using something akin to a micro virtual machine. So it's essentially a virtual machine, but it's been stripped down to its very, very bare essentials. And what that essentially means that it means that virtual machine can boot up, exceptionally fast, as opposed to a traditional virtual machine, which tries to emulate all the various kind of real-ish hardware. And so therefore it's a lot larger and takes a lot more time to boot up. But a micro virtual machine is stripped of all of that and so can boot up very quickly. So that's what micro VMs are essentially. So they are virtual machines, but they are very, very stripped down for performance sakes. And obviously in the cloud, this kind of isolation is amazing because Docker, whilst Docker is amazing, you have to understand Docker is more of an abstraction. It is not the same thing. It's not going to provide the same kind of isolation as a virtual machine would. And one of the key things you can remember is that you can run inside a virtual machine. You can run Docker, but not the other way around. I mean, theoretically you could, but it would be through some sort of things like QEMU and doing software emulation, but that's not the same thing. But essentially, a VM is greater in terms of the isolation, and inside of a VM you can run containers. And in fact, I think most modern clouds, that is how it's done behind the scenes. So when you're running your container image, it is being run inside this isolated virtual machine. So anyway, to actually run this krunvm, which is it's just a nice little CLI tool that is used to kind of manage and run and create and all that kind of stuff. But underneath, it uses libkrun. So libkrun itself. So if you wanted to just compile this, you're not going to be able to just compile it because it depends on libkrun. Now libkrun itself, if you look at here, so this is libkrun, and when you try to compile this in itself requires, if you go down here into the requirements for building it, itself requires libkrunfw. So if you go to libkrunfw, you'll see that what this does is essentially it builds the Linux kernel, but as a library, which is kind of insane and very interesting. And so in order to run this, you need to have Python 3, and Python 3 specifically, you need to have these tools. And that's not actually completely the end of the story, because when I started building, this started failing, because I started off essentially at the top of the tree effectively. So I tried to build this failed. I then tried to build krunvm. That failed, of course, because it depends on this. So then I tried to build libkrun. That failed, of course, because it requires libkrunfw. And so now we're here at this stage, and I said you have to build the SE variant specifically. So if you look at here, it tells you as part of the in terms of building, it requires when compiling, you have to make sure it is the SEV variant. SEV variant. So that is, yeah. So it says the requirements, and before you can do sudo make install the SEV variant of the libkrunfw, which provides this particular library. So essentially all this boils down to is we require this library here, this dynamic library. Once we have this library built, in theory we should then be able to compile and build this one here, which is the libkrun, which is a library. And once this library is built, we can then finally build this command line utility. So yes, it is it is quite a few steps in terms of dependency, and there is it's a long dependency. It's not as simple. It isn't as simple because we're talking about the entire Linux kernel here that we have to build and build it into effectively a dynamic library, which we can then embed into this other project, and then we can then use for the build output from here, but finally into this. So let's go. And so we're now inside of the libkrunfw, and we should be able to do make sev equal to 1. This is as per the documentation. So now it's going to try and build that, and this is now trying to build the Linux kernel, and it probably will fail. It will fail because there are who knows what kind of dependencies and what kind of things that are required. But on top of that, all of this is happening inside a virtual machine itself. And in fact, to be honest, I'm not entirely sure if I have nested virtualization enabled. If I don't, this thing will run super slow when the actual krun and this one actually. So when krun or krunvm is run, because it will create a microVM and try and run that, it would essentially be a nested virtual machine, because this entire screen that I'm recording is inside a virtual machine itself. So I would be running essentially a virtual machine inside a virtual machine, and that's perfectly possible if you enable nested virtualization. And I cannot remember if I have done that in my hypervisor essentially. So we will find out. But anyway, let's go back to the build. There it is, chugging away, building essentially the Linux kernel and building that into essentially a dynamic library, which we can then embed into libkrun. So this is the libkrunfw, whatever the FW stands for, I'm not sure. But anyway, it's building that, and hopefully if it successfully builds, we can then install it onto our virtual machine, or this instance, and then we can, so we have to build the first one, hopefully install it, and then we can then build the second one, which is a libkrun. If that builds, we can hopefully install that, and then finally we can build our actual target project, which is krun. Yeah. So there it goes. There away it goes, building stuff, and this is pretty boring actually, but it's also exciting as well, just to see how it builds. So if you never built the Linux kernel, this is kind of what it feels like, looks like. I mean, I think you use a specific script, I think build script or something. But you have to define a whole lot of things, and you have things like hardware layers and all sorts of things. So there's a whole lot of optional, it's almost like a whole lot of configuration that you can do to target how you want that kernel to be built. And this is where you can include things and exclude things, and it's just, the whole thing is just the fact that there's almost like a custom build because the actual code base is so complex and so big, and there's just so much stuff that it has to build. But it's still interesting, and we will just wait here. It's almost like, just like watching paint dry sometimes. Right, so where have we got to? The kernel power. So it's building that. Building the network. Now, if I go back to the project, we'll let that build actually, because it's literally just boring. I mean, it's just building. So if we look at so this is the actual libkrunfw, and so it says here libkrunfw is a library building a Linux kernel into a dynamic library in a way that can easily be consumed by libkrun. So obviously, this is the underlying dynamic library, which is which libkrun itself is dependent upon. And by having the kernel bundled in a dynamic library, libkrun can leave the linker and the work of mapping the sections into the process, and then directly inject those mappings into the guest without any kind of additional work nor processing. Okay, that's fine. So if we go back to libkrun is a dynamic library that allows programs to easily acquire the ability to run processes in a partially isolated environment using KVM virtualization. It integrates a VMM, which is a virtual machine monitor, the user space side of the hypervisor. with the minimum amount of emulated devices required to its purpose, abstracting most of the complexity that comes from the virtual machine management, offering users a simple C API. So possible use cases: adding VM isolation capabilities to an OCI runtime. So essentially a Docker container. And implementing a lightweight jailer for serverless workloads, which is very interesting. And bringing additional self-isolation capabilities to conventional services. Think of something as simple as chroot, but more powerful. And I do always like to look at the limitations around here. So this was quite interesting actually. It's saying that in libkrun networking is implemented using a novel technique called transparent socket impersonation, or TSI. This allows the VM to have a network connectivity without a virtual interface. That is really interesting. Hence, VirtIO.net is not among the listed supported devices. This technique supports both outgoing and incoming connections. It's possible for user space applications running in the VM are able to transparently connect to endpoints outside the VM and also receive connections from outside to ports listening inside the VM. I mean, I don't know what this particular magic is, because obviously when we run a Docker container, we lean upon the network's isolation features that it provides in order to provide essentially a virtualized network stack. Well, it's not a virtualized network stack. It has its own virtual bridge that it connects, VF pairs that it creates inside a namespace. And this is I'd not come across this. So this does sound a bit like voodoo. So how is it possible that this MicroVM, transparently is able to talk to the outside world? So if someone out there who's an expert on this networking and knows a little bit more detail about transparent socket implementation, I would love to hear from you guys. But this is kind of, to me, seems like almost like magic. How does that work? But yeah, it's saying that TSI only supports impersonating inet sock dgram and obviously sock stream sockets. This implies it's not possible to communicate outside the virtual machine with raw sockets. That could be a potential issue. But yeah, so I think maybe it's in here. Maybe the word impersonating. So somehow it pretends to be that sort of raw socket or something. I don't know. I don't know how that works. Okay, so back to our actual compilation, and it's still chugging away. So now we're under sort of the memory side of stuff. Looks like the kernel, the certificates. The root certificates, I presume that's what's being built over there. And the memory management, there is so much of that. I mean, that's quite a big chunk of the kernel is that. What I may do is I may edit this video. I generally don't like to edit my videos, and I like to have the entire raw kind of video. But this is so boring that I may just snip this bit out. But we'll see. We'll let this run, and of course you can also just forward this part of it, because I don't know how long this is going to take. I mean, let's say if it takes an hour, that would be an amazing amount of patience for someone to sit there watching this. But I presume if it was, I mean, I did actually notice, if I go back, I did notice somewhere where they said for a certain, I think there's a specific reason where they, in the known limitation, that's it, to save memory, the embedded kernel is configured with config nr CPUs equals to h, which limits the maximum number of supported CPUs to 8. If the kernel runs in a virtual machine with more CPUs, only the first 8 will be initialized and used. So there's a hard cap, yeah. So compiling the kernel, Linux kernel, obviously, is a pretty intense task, and I guess what they're saying is, in order to save memory, so that the memory doesn't, so your memory doesn't essentially completely blow up bottleneck. I think what they're doing is, they've capped it here internally to 8 CPUs. I think them running 4 CPUs on this virtual machine. I can't remember. And so yeah, that it'll be capped anyway. It doesn't matter even if you threw like 32 CPU cores or something to try and speed this up, it will not work because they've capped it. Okay, let's have a look. Let's go back. Yeah, it's still building, I guess, the file system now. So the memory management's done now, and it's now building up the file system. Away it goes. Oh, look, FSI node. That's interesting. There's a whole video recently, and I think the Primogen reacted to that as well. I think it was like Faster Than Lime who originally posted about. It was an interesting story because essentially the Rust for the Linux kernel. There was a sort of, I guess, like a talk or something where some of the guys who were working on, I think it's like the Bcache file system or something like that, they were essentially trying to show the benefits of safe Rust, essentially, and the idea that how, if you look at C, for example, you have all of this implicit knowledge, that is just has to be fully understood by the person who's writing that particular code or device or whatever. And the issue is that that's not compiler enforced. And of course, this is why we can have so many issues in the code base, is because it depends on the discipline of the C developer. And really all they wanted to show is really a simple kind of demonstration of the power of essentially offloading, if you like, that implicit knowledge and then putting that into the type system. So lifting out all of those granular like knowledge, if you like, into the type system. And then once you do that, how much easier life is, because then you have strict compile time guarantees, because the compiler will enforce you. The compiler will force to make sure those things that have been embedded into the type system are essentially they're always adhered to, and also because you remove so many undefined behavior, because we simply do not want that. That's where a lot of bugs and issues can creep into. And what in that entire talk that they did, they couldn't get very far because they were really almost like, I think they got into 2 slides before some of the older C developers got very angry and they were very agitated, and I think one of them shouted out something along the lines of, "You're not going to convert all of us to Rust," essentially. And it was really kind of sad, actually, because it wasn't the case that it's not an attempt to try and convert all of the C developers. That was not the intention. The intention was, look, we have to think about the future in terms of kernel development and how that proceeds, because we cannot have the case where all of this knowledge just sits in the heads of select few developers, essentially. That we in the industry, this is something known as the bus factor, which is essentially how many developers have to be. I know it's kind of gross and kind of violent, but how many developers have to be run over essentially by a bus before your project is in serious trouble. And obviously the Linux kernel has thousands of developers, but I think, in terms of contribution, of course, but I think there are only a few core sort of kernel developers. Obviously there's quite a few, and it wouldn't be in immediate danger, of course. However, it could be seriously impacted. And obviously when you have, if we have the possibility to have a safer language that can take and encode a lot of that complexity into the type system, and then we can then have compile backed guarantees of that would have a huge cascade in terms of stability and robustness, and over the entire code base, in terms of just the ease at which we could do refactoring, the ease at which we could do maintenance and expand on features. At the moment, everything feels like it's all tacked together with bits of string. Essentially, you have this big ball of, I wouldn't call it spaghetti code, but you have this mountain of essentially this huge monumental structure, if you imagine. But they're all like tiny little toothpicks that have been sellotaped together, and it's so fragile. And if you make a tiny, if you remove a tiny bit, then it impacts the whole thing, and in very subtle ways. We want stronger foundations, essentially, and That's not to say that the entire Linux code base can be converted overnight. That's not going to happen. Absolutely, it's not going to happen. It's going to be a gradual, sort of phased kind of transformation, but it has to start somewhere essentially. And yeah, and so it is kind of disheartening to see that kind of reaction from these core or some of these core C developers. And yeah, I mean it's a difficult one because we can empathize from their perspective. They have a working way of approaching, and suddenly there's all of these newfangled language coming along, and I wouldn't say they're kind of threatened about it, but they don't fully understand it and they don't like it, and it's like they just see I believe they think it's just sort of a lot of extra complexity, and they're struggling to understand why for example they would need something like this when the way they have approached it for them seems to work. And yeah, it is, I guess, bridging that to say, look, it's not to say what you're doing is completely wrong, but we're starting to have languages and tools that can help, and that's the main thing. It's about help. It's about a better approach. Essentially, we don't have to build something or refactor some code or add some new code, and then have to worry about spending a lot of time debugging it and having to go back again and again and again and having to do so many checks, so many defensive coding. I presume a lot of that is probably in these kind of code bases, there would be a lot of defensive coding. And defensive coding is a strategy where I think you see that would happen in languages that have very weak type systems. Now obviously, there is a whole spectrum of type systems, and I think type systems that tend to be weaker, the developers will kind of almost, in order to cover that, the weakness, they'll cover that using what is called defensive programming. That's where there's so many checks and assertions and things like that are added, simply because you don't actually know what your state is, what specific state at any moment in time is. And again, that points towards the fact that you don't actually have the type system being smart enough to encode those states, or the language doesn't have the way to express that, and that's a problem. And that's where languages that have better type system come in, essentially, because you can now encode your program state. And don't want to throw out big words out there, but I think they did, and I think the Primogen also made note of that as well when they essentially talked about ADTs, which is algebraic data types, and obviously big fancy words like that would, if you have that amongst sort of older C devs, that would sound a little bit scary and hairy or whatever, but they're not. I mean, they do. They're sometimes, and unfortunately, when you have slightly more advanced type systems and whatnot, they can use sort of these fancy words, but they're almost kind of like a bit of a jargon, and they're not really that scary once you sort of strip away and find out what it is. I mean, if you think of sort of like a kind of an ADT, you can think of it kind of like a sort of enum on steroids, essentially. But really what it boils down to essentially is to say that, look, we can define these states in the type. We can define the states in the type, essentially, and then once we do that, we can we can use that we can leverage the compiler to make sure all of those states are dealt with in terms of the code branches, if you like, and things like we have in Rust, we have the match, and so the ADTs and match, they go almost like hand in hand. So pattern matching and ADTs, they work so brilliantly with each other, because obviously the pattern matching means that there's an enforcement there, that every branch, if you like, every branch of that particular program state, as has been defined, has to be dealt with, essentially. So there's none of this. Number one, there's none of this implicit knowledge that's stuck in the head of the developer, and in terms of all the various different states. And number two, you know exactly what particular state, because you've defined that, and the compiler is going to make sure that they're dealt with, as I said. So it's fully defined and fully known, And so far, you don't have this. You don't require this defensive coding with assertions and all this kind of stuff, because, as I say, you don't have to. If you didn't have those states defined, you couldn't be entirely sure at any given time what the state is. But then, if you lift those inherent implicit sort of knowledge, and you sort of embed it into the type system, then it's right there. So anyway, now it looks like it's doing, I guess it's done the crypto stuff, and now it's compiling the block, all of the sort of low-level block devices. So these are like disk drives and stuff, not just disk drives, anything that relates to like file system devices and things like that. And it's going through, build. Very, very boring. Let's actually watch let's watch a video. I think we could watch a YouTube video while that's going through. Multitasking. Yeah. So actually that probably would have an impact on the build. So let's see what the Primogen is up to. Wow, even my typing is slowed down. Okay, let's come up. The Primogen. There you go. Yes, all is block. I don't want notification. Right, what the Primogen? So what's he doing? It's all over. 2 idiots and 1 keyboard. Why more people don't use Linux? Do more people need to use Linux? I don't know, maybe. I mean, I think if people find Linux useful, they should do. I think people will generally sort of go towards it. I did react to this before. Well, not completely, but I mentioned this. There's one video that I did earlier. There was one that I saw from him. Where is his actual channel? The Primogen Time and Primogen. So he has 2 channels. Interesting. Maybe it's this one. Maybe. Let's have a look. The Primogen. So what videos does he have? Click on the videos. I really hate this autoplay thing. Let's have a look. Videos. Latest. I went to DEFCON. Art developers. Okay. Maybe it's the other one, because I did notice he did one. He did one recently talking about when he was talking about the C developers that were he mentioned a few things in that. Just trying to find it. You can't do this. I fixed Git. Our developers okay. Maybe it's the other one. Let's have a look. Maybe it's his other one that he's got. So let's go back. Wow. Don't compile the Linux kernel whilst also watching YouTube videos, I think is. Okay, videos. Let's have a look.
Shamir, secret.
Stop. Nobody cares. Blah, blah, blah. Nobody cares about your technical GitHub projects. Why don't more people use Linux? That wasn't the one. Stop being so dumb on Twitter. I do like his thumbnails that he uses. They are pretty clickbaity. So where was the one about? It was about that Linux code. It was about that presentation that was done. So where is that? I think it might have been a few days ago. So my gosh, he just produces like an avalanche of videos, doesn't he? So it's very difficult to keep up. And let's have a look. Rust a month ago is Java is better than Rust. Okay. Yes, interesting. That's definitely clickbaiting. Not invented here syndrome. That's not the one. Walking away from JavaScript. I hate my 80% of developers dislike this job. Okay. Okay, probably let's use the search rather than trying to search through. So it was called Linux. Let's have a look at all of his Linux videos that he's done. think it was Rust as well, kernel. Yeah, okay, this is the one. What is wrong with Rust and Linux? Question. Oh, hang on. Whilst we do
I know we've looked at this.
Let's pause this for a second. Let's go back to our compilation. My God, it's still compiling. Okay. Yeah, let's watch this video while that's doing. I'm gonna bump down the resolution to something lower. Let's do 480. Nope, we can go lower. I'm gonna watch this in 240. I don't think, yeah, I'll be fine. And bump the volume down because he is very loud. Right.
I know we've looked at this a little bit, and we watched part of this presentation, I think, but I had no idea exactly what was going on because we only started right here. But this is kind of wild. So apparently,
as you can see, I'm not.
This was a presentation on the file system. This is what I'm kind of gathering for the Linux. Dude, the fact that the Linux Foundation posted this is crazy.
Kent.
And so,
but I'm the one who is actually sending the patches for the file system abstractions. So we decided I'd show you guys a few slides and then we jump into discussions. Kent also has a list of things in addition to what I'm going to show here. I'm going to try to be.
Sorry, my inner monologue just got so excited about this. Louder? Yeah, my bad. I didn't have it louder. But I did watch a little bit of this. We watched up here, and we'll jump up here. But apparently, he only got through 3 slides, is what people have said, and then could not get further because people were so staunch on what was happening, which is just kind of a whoopsies.
I love you.
My bad. Left the alerts on. Get wrecked. I just had no idea it was this bad. I guess I just didn't really understand. Rust, always drama around this cult. This one I actually think is potentially C devs issues. This might actually be a C dev.
Yeah, I don't know if it's a C dev issue, but yeah, it is essentially that that kind of friction between, I guess, the C devs being very scared of new things, essentially. Really, that's kind of what it boils down to. It's kind of sad, as I was mentioning earlier, but yeah, let's continue.
Dev issue.
To be brief, so we can spend most of the time on the discussions. Okay.
Okay, hold on. Let's have a look at that compilation. Yeah, that's still compiling. Where did it got to? Ooh, drivers now. Video drivers. Very fun. Okay.
So a quick status on where things are. For those who may not be following this, I sent an RFC patch series sometime last year, and there's some links here. And,
we're going to see how long it takes for him to get interrupted.
For things to change, and I made those changes back in January.
Sorry, I'm just going to keep jumping back and forth because I want to kind of keep an eye on, and I really, really do hope that the Linux kernel compiles into a dynamic library. That'd be pretty cool. And but yeah, apologies. So if you see me jumping back and forth, just yeah, ignore.
And I just posted them on Zulip. I didn't actually send them to the mailing list, but I did it this morning. I was planning to send them earlier, but I decided to wait until the morning after a few beers last night.
It's a good move. Good move. By the way, he just gave you a very great piece of wisdom. Never communicate after a few beers. Okay.
Of the abstraction. Basically, in requirements that the code have in the type system. And this allows us to catch more bugs at compile time. And I'll show you quickly a couple.
Yeah, and that's exactly as you mentioned, moving a lot of the things into the type system, encoding a lot of knowledge into the type system so that the compiler can essentially, you can have compile time guarantee. And that's really what the whole talk was about to show that, to essentially show, I guess, the rest of the kernel developers and C developers and whatnot about the benefits and advantage of it. But unfortunately, they couldn't get very far without arousing the anger of the existing C developers. Let's have a quick look at our. Talking of C development, this is the Linux kernel literally being built as we're watching the video about Rust inside the Linux kernel. Let's go back.
A couple of quick examples afterwards. It also allows us to automate some tasks that are not.
I like that we have the pre-knowledge of what's about to happen, and he's just like, I'm going to show you guys a couple of examples afterwards. No idea what's about to happen. Just none. Just not even ready at all for what's about to happen. What time did I wake up? 6 a.m. on the dot.
Very easily automatable in C, and I'll show you a small example later too. And the result of these two things is that we have a more productive developer experience when we are writing file systems in Rust or code in general. You want to add something, Ken?
You got to be careful. See how he's yapping? See what he just did there? When you tell C devs who are used to doing everything themselves that you'll have a more enjoyable coding experience in a different language, oh, you just yap into them, okay? These guys have been writing C longer than I've been alive. That's yap. This is yapping at that point.
Oh. Yeah, so as I said before, we get more bugs caught at compile time. We spend less time debugging these issues. So when I talk about developer experience, I'm not just talking about the time you sit down and you spend writing the code. I'm actually talking about the time afterwards when you try to deploy the code and there are issues and you have to investigate those perhaps in production. So you save a lot of time by catching those bugs earlier.
I thought he was saying that Rust had production bugs. We all know that the number one reason why people use Rust is that you write bug-free code, right? Because that would be really, really confusing if that wasn't the case. I mean, Rust in shambles at that point. The amazing part of this whole exchange is the realization that apparently nobody really knows the FS interface. There's one guy that knows it, and it's all in his head, and the day he dies, there will be something like 6 months to 14 years of no improvements on the file system. And that's that.
Yeah, and that's scary. That's essentially that is kind of the point of building up and trying to extract that knowledge and putting it into the type system. And yeah, it would be kind of scary actually, because that's just one individual. What about other individuals as well if they suddenly pass away or die or whatnot? And well, eventually everyone will die. But that is an issue. You cannot just have implicit knowledge floating and just floating around in the heads of a few individuals. That is not a good coherent strategy for the long term. It might be okay for the short term, but certainly not for the long term. But anyway, let's quickly flip back and have a look. Ooh, something else happened here. So some errors actually. So discarding const quantifier. So yeah, it's still compiling, but there were some warnings, I guess. So I guess that's fine. Struct virtual IO device, but argument is of type. Okay, these are just like, I guess these are just compiler warnings, not actual, just warnings that you can potentially ignore, but something to be wary of, I guess. Let's go back. Okay, let's continue.
And of course, we also have fewer memory-related vulnerabilities because of the undefined behavior guarantees that Rust offers, and those sort of eliminate, modulo some bugs in the compiler and abstractions. It eliminates memory safety issues.
In my career, I've seen a lot of like massive 2 weeks, all hands on deck bug hunts, and we all have. Those kinds of bug hunts suck, like and I've been doing a lot of work in bcachefs to try to eliminate those and come up with better assertions and so on. Rust does a lot more than anything I could do. The two main threads that I've been pushing on, and I'm going to be talking more about the bcachefs BOF, are undefined behavior, eliminating undefined behavior, and also better reflection. You can't debug if you can't see You can't debug if you can't see what's going on. Rust has some really nice provisions with that are kind of secondary, but very useful. And lifting us, we don't talk enough about assertions in the kernel because reasons, but the end goal, like what I see.
Why don't they do assertions? I know the man's so he's disappointed and he's trying to you can see that's called an inner monologue, people. That inner monologue's yapping, going, don't say it. You're about to say something. The moment you say this, you know what's gonna happen. Like, see, he knows what's about to happen here.
In a couple decades out, kernel development is going to be getting a whole lot.
So yeah, possibly. I mean, the way I read that is essentially he is frustrated with the way of doing C in terms of, as I was mentioning about bug heights, and it's kind of like I completely understand his frustration. It's the sense that once you have sort of experienced working in it, it's like if you were suddenly, if you all you've ever known all your life is to use essentially maybe a knife and fork or something, and you've only, or let's say just a handsaw or something like that, or just even a butter knife or something, and you've always cut down trees, which is a ridiculous analogy, but that's all you've known how to do, and then suddenly one day you discover a chainsaw, and you suddenly realize, wow, you can cut this tree so efficiently and so quickly and so productively. Why? And then if you're then told to go back to using a butter knife, you would be in this kind of depressed, or not even depressed, but you would be so reluctant. And that's all of these deep sighs of breath that he's doing is because of that frustration of having to, once you've experienced that kind of having that type safety, having all of that safety, memory safety, and all that kind of stuff because of the more advanced type system, then having to go backwards. It is something that it's sort of like, it's like really, that's what it is. And I think it's not about him talking about, this is his inner monologue where he's thinking, I'm going to have a resistance, a pushback from the C developers. It's not that. I think that, well, maybe it could be that, but I don't think it is. I think it's genuinely that kind of frustration of like cringe/frustration of knowing what's possible. But then perhaps maybe it is some of that inner monologue in the sense of how do you then explain to someone who has never experienced the productivity of a chainsaw over a butter knife? How do you do that? I can probably understand. Hang on, let's just have a quick look. Now it's doing some firmware stuff. It's building some firmware stuff, compiling that. Okay, this is going to take hours, maybe, maybe even run out of watching video materials. Well, maybe not, because we've got all of YouTube, so there's enough things to keep us amused. Anyway, let's continue.
A lot easier over the coming decades. The end goal that I want to see is a programming experience where we've got a language where we can practically do embedded correctness proofs, where we know when we write the code that the code is correct, so that when I finish a project and move on to the next thing, I know that I'm not going to get yanked back to that previous project debugging things. That's not fun. It's not productive getting yanked off to, the code that should have been done months ago.
By the way, Rust cannot guarantee that. Rust can guarantee you things about memory that are correct. It can guarantee you various stuff, but it does not guarantee that you've written a correct program. And this is one of those things that people keep getting incorrect when they talk about Rust, which is there is no replacement for human stupidity. And this includes LLMs, because LLMs...
No. So, I think the Primogens kind of missed the point. I don't think... So actually, if I pull up the transcript, sorry. Where is the transcript? Let's pull up the transcript, because I think he's kind of missed what he said here, or he's misunderstood, or he's misinterpreted it when it loads, if it loads. Okay, let's go back. Yeah, so if we go to 621, if we click here, oh, look, it says here, the end goal, what I want to see is a programming experience where we have got a language where we can practically do embedded correctness proofs. So he's not saying, and I think this is a misunderstanding or misinterpretation by the Primogen, this individual, the speaker, is not saying that Rust is, the Rust compiler does correctness. He's saying that the end goal, eventually, the language we can practically do embedded correctness proof. Not saying that we can do that now. So, yeah, it's not to say the Rust compiler, if you write some code in Rust and it compiles it, then you already have correctness, because it's not that. That's not, and he absolutely wasn't saying that's what it was. He was saying that as an end goal. Because I believe if we look at, there are external tools, Rust correctness. I think there are tools that you can apply for Rust correctness because these are like part of formal verification 5 automatic verification for tools. Let's have a look. I know there are a bunch of them out there, so let's have a look. Cargo fuzz. Well, that's fuzz testing. That's not correctness. What kind of? I mean, the log rocket, they do sometimes okay articles out there, but actually, hang on, let's have a look. What's the compiler doing? Compilation. Our Linux kernel is up to net Ethernet tool. How? Yeah, it's massive. It takes ages to compile the Linux kernel. Let's go back. Okay. This isn't the one prop test. This is about property testing, and this is not automated verification tool versus. That's interesting. Right, interesting. So Versus is a tool for verifying the correctness of Rust code. Developers write specifications of what their code should do, and Versus statically checks that the executable Rust code will always satisfy the specification for all possible executions of the code, rather than adding runtime checks. Versus instead relies on the powerful solvers to prove the code is correct. Versus currently supports a subset of Rust, which we are working to expand, and in some cases it allows developers to go beyond the standard Rust type system and statically check the correctness of that code. For example, manipulates raw pointers. So we have here Versus example no verifying root module, post condition not satisfied, failed this post condition at the end of the function body or body due to previous errors. So what is the status? Is an active development. So yeah, they're still building around on it, and you can have a look at the documentation. So yeah, I mean, it gets into sort of things like dependent types and all that kind of stuff, which you have in total languages like Idris. So if we look at Idris, I think it's like Idris 2 now. I can't type today. Idris 2. Come on. You can load. And Idris, the programming language. So yeah, Idris is a purely it's loading. Let's get rid of this. Idris is a purely functional programming language with dependent types, optional lazy evaluation. So it is, I think it's strict, but you can add in option, which I think is, it's going to be a bit of a controversial take, but I think is the right order of things. Having everything completely lazily evaluated all as the default is kind of crazy. And features such as totality checker. Idris may be used as a proof assistant, but is designed to be a general purpose programming language similar to Haskell. Idris' type system is similar to Agadas, and proofs are similar to Cox, including tactics, theorem proven function procedures via elaborator reflection. Compared to Agda and Coq, Idris prioritizes management of side effects and supports embedding DSLs essentially. Idris compiles with C, which is interesting, relying on a custom copying garbage collector using Cheney's algorithm and JavaScript. There was a backend for PHP, which I found absolutely hilarious. So Idris could be. Let me see if I can find it. So Idris PHP backend. I'm not making this up because I saw it a while back. Let it compile. Idris. Look at this backend. This is hilarious. So Idris. This is by Edwin as well. So the author of Idris, or the creator of Idris to PHP backend. Please don't ever use this. Yeah, but it's absolutely crazy. Why? I'm glad you asked. While I'd never recommend using this for anything real, there is a reason why making this has been an interesting exercise other than it being a bit of fun. These days there are a lot of platforms on which we might run our software, such as JVM, .NET, JavaScript in the browser and so on. Apologies, so I had to take that call, but essentially since then the compilation is completely completed. So that's fine, and I can actually demonstrate that because it's actually installed under here. So we can go into local and lib64. And here you can actually see libkrunfw sev so 4.3.1, and then these are sym-linked to each other. Now that's all fine. That's grand. And if we have a look at that, so for this particular libkrunfw, which is the Linux kernel but compiled down to a dynamic library, that obviously took a long while to compile and everything, but it did successfully compile, and I have that here. Unfortunately, if we go back to our desktop, and if we now go into libkrun, which is what we was trying to build, if we try to build this, actually, let's have a look at the instructions for this. So on the build instructions for this is, if we have a look, so we need the libkrunfw, which we have successfully built, and there's other things for working Rust toolchain. Yes, we definitely have that. C static libraries, I'm not entirely sure. glibc essentially -static in Fedora. I don't know under Arch what that is. Probably may not have that. And patch elf. Now I haven't seen it complain about patch elf. I presume it would have failed with that if we didn't have that, and it did seem to be okay without the glib static. I'm not sure, but anyway, apparently you can just do make install, and it says the requirements. You need the sev variant of the libkrunfw, which provides the library. We have that. We've built that, which is fine, and OpenSSL headers, OpenSSL devel. I believe I have that, but if not, I can certainly do that. So that's the installation part of it. But building and installing Linux generic variants, you can just do make. So if we do just make, you'll see that it will try to compile it, but then it then fails to compile, and because it says that it essentially can't find it, it might be because it's expecting it in a certain particular path and it's not finding it there. That would be the issue, but this is as far as I got. Essentially, I would have to tinker around with it a little bit more. I'll just show you anyway. It's not going to, it will not compile because this libkrun didn't compile before when I tried it. Not because I don't have this libkrunfw, which is the requirement. This is the library, essentially the dynamic library, but this is the Linux kernel. This is the Linux kernel compiled down to a binary, a dynamic binary. But yes, it failed. So it tries. It's a bit annoying that I don't get the verbose kind of debug here, so I'm not really sure. But yeah, this is how it compiled. It failed before, but essentially the linker couldn't find lkrunfw, which is the dynamic. This essentially this binary here, it can't find it. So I will have to tinker around, and I could potentially look at the make file itself. I'll have to look through here and see what, and go line by line and sort of figure out why it's not finding it. My assumption would be things like, yeah, where's the actual binary, krun binary, libkrun. I'd have to go through and have a look at that. So apologies if this particular session was rather chaotic and it sort of jumped around, but yeah, this is a very interesting project. I will keep at it. I may do a post video update once I successfully get all of this compiled and working. It is a shame there isn't like a Docker container that's completely, and maybe I should do something like that. Maybe I should wrap all of this into a container, because it would be absolutely amazing and nice just to be able to just do cargo build essentially and have that. But this is a complex set of dependency. It is quite a complex project, of course, but nevertheless, it is very fascinating. And yeah, that is all for this particular session. And until the next one, I'll see you on the next one.